So this is the introductory module, or the primary module for triple integration. Okay. And triple integration is the last major new thing in terms of what we're doing in terms of integration in vector calculus. Once we have triple integration, then we're ready to move on to divergence theorem. That's the last major theorem. We'll look at other coordinate systems, and that will kind of round this out. The module, the written module that I'm covering here is called triple integration. And this is covering material in section 915 of the textbook. And you can go to the textbook and it has more background, not derivation, but rationalization of the process there. Here we're going to just talk through it and then look at examples and just do one primary example today. So when I said triple integration, I almost caught myself, or I did catch myself, calling it volume integration. So this is even more than double integration. This language comes up where we are doing an integral over three variables. Okay, so an integral in three-dimensional space. It's a triple integral for that reason. Sometimes you can think of it as, well, we're integrating some function over a volume, because a region in three-dimensional space would be a volume. I don't like to use that language if I can avoid it, it's hard to avoid, because we're not doing a volume calculation in general. Sometimes we are. Actually, the first example I'm going to do is a volume calculation, but like always, that's a special case. That's the case where the integrand is 1, and we're just integrating a volume element. Triple integration in general is some function that varies over three space. It could be a vector function, as a result we'd get a vector answer, or it could be, for us, in almost all the examples we're going to be looking at a scalar function. And if vectors are involved, as they are in the divergence theorem, we'll be calculating, say, their divergence of them, and then calculating that, which is a scalar function again. Okay, so in general, a function of three dimensions. I've written this as 1, 2, 3 integrals over some region D, a three-dimensional region, of a function I've written as a function of x, y, z. It doesn't have to be x, y, z. It doesn't matter the coordinate system. It matters how we do it. But we'll look at, certainly, after Cartesian, we'll look at cylindrical and then spherical coordinate systems. So I've written x, y, z at this point just because we're going to start with that. But in general, that's not the case. It doesn't have to be the case. And this is the general schematic of the process. We've got some three-dimensional region D. Okay. In principle, it could be infinite. I could have infinite and have an indefinite triple integral. We don't do many of those. But certainly when we get into integral transforms later, we do. So that's allowed. But in general, we have, for us right now, we're going to talk about sort of finite regions. Okay, so let's imagine this blob, three-dimensional blob, hanging out here in x, y, z. Okay, it has a top, it has a bottom, it has sides, it has a front and a back, if you want to think of it that way. So if you think of the top in terms of z, that's kind of what the language suggests. The function that describes the top of this blob, we're going to call f2, which is a function of just x and y. It's a height z over the xy plane of the upper surface of the blob. The lower surface of the blob would be f1, xyz. It's another function, a height of the lower surface over some region r in the xy plane. Okay? So the top surface and the bottom surfaces are z's as a function of x and y. Yeah? This is one way to look at it. Sometimes f1 xy is 0, and then we're just looking at the height of this thing over the xy plane entirely. So it's a region from z equals 0 up to f2. But in general, the bottom can be another function, and sometimes it is. Often we talk about things in the first octant or something, and one of the limits is 0, but that's just a special case. So when you think of this thing projecting down, if we think of, we're going to integrate this along z, so we compress it into a two-dimensional region. Think of it as casting a shadow. If you shine a light down, there's a region r in the xy plane that remains. Once we integrate between z bottom and z top, you squish it, and now you have just a two-dimensional region. Call that r. And now we're doing double integration like we did before. This region r has a top contour and a bottom contour. We'll call the top part y equals g2x, some general function of x. The bottom curve is g1, some function of x. g1 could be 0, could be, but doesn't have to be. Okay, so we compress integrate in z to get a 2D. Then we compress integrate along y, and then what you're left with is something that varies between, say, a and b. Okay, and then finally, we integrate that final thing between a and b. So it's iterated integration like we've done with double. That's why triple integration is not that shocking. It's just another layer on top of double integration. Double integration was the first one that had iteration in there. You have to make choices of which to do first, etc. So this is not so surprising. I hope it's clear that when you have this blob, doing this as compress integrate along z, then compress integrate along y, then finally x is one of 6 choices. You could also compress integrate along y, then z, then x, or compress along y, then x, then z. Even in this one, we compress along z, we could then go with x, then y. So there's a series of different orders you could do this in, and depending on the problem, you will choose one or the other. Usually one is more obvious given the problem definition. Once you have these functions, the top surface function, the bottom surface function, the top curve function, the bottom curve function, and the finite limits, then you set up the iterated integral with limits of integration defined by those functions. You have your integrand, which is some function of x, y, z, okay? And then you proceed. We keep our convention where the first integral is the innermost differential, the second integral is the next, and this one is the last. So it's almost like bracketing. This integral iterated. When we're done, the z's will be gone, and we have a function of x and y. Then we do this one. We integrate out y. When we're done, we'll have only a function of x. And then that function of x is integrated as a definite integral between a and b, and we end up with a number, right? When we're done, no x's, no y's, no z's. Okay, I get it. So let's do a simple example. This is actually the first example out of the textbook that talks about this triple integration. Find the volume of the solid. So despite what I said about not all triple integrations being volumes, we're going to start with the volume. We always do, because it's the easiest one. The integrand is 1. So find the volume of the solid in the first octant. So first octant means we're limited by x0, y0, z0. Bounded by z equals 1 minus y squared, y equals 2x, and x equals 3. Okay? Always, we sketch this out to understand what we're going to do here. So z equals 1 minus y squared in 3-dimensional space is something that doesn't depend on x. So this looks like an inverse parabola. So we have a height z of 1, right? When y is 0, x, z is 1, and it's a parabola downward, raised up by 1. So when y is 0, z is 1, we're up here, right? And this curve here, right, is z equals 1 minus y squared. It doesn't depend on x, so it's like a cylinder that extends along the x-axis. It's true that this would be plus minus, but we're stuck in the first octant, so we have a plane here that takes away that minus y component, right? Because this would be a parabola defined for both plus and minus y. So that's this shape, okay? It extends from plus minus infinity along the x direction, starts at z equals 1 and goes down to minus infinity, but it's capped off by z equals 0 and x equals 0. Oh, sorry, y equals 0. Okay, so that's great. What caps this thing? Well, we know we're capped at x equals 3, so that puts a plane right here and stops this thing. And then we know that we would be capped at x equals 0, but we have another limit. We have y equals 2x. That's a plane, right? First order in x, y, z is a plane. Again, doesn't depend on z, so this is like a curtain that's hanging in the vertical direction. It goes from plus and minus infinity along z. And it cuts here, right, at x equals 0, y equals 0. So it cuts right down this plane and then comes out at an angle, okay? Y equals 2x. So we have this cut here. So this is the region we're talking about. This is the top of it. It's at an angled plane on this side, a flat end on this side. This is one of those cases where it's worthwhile to now just draw what this thing looks like from above. Okay? So over here, I just draw now x, y, so z would be coming into and out of the board. Let's just look down on this thing, just to be clear what these limits look like. So x equals 3 is this plane. This angle here is y equals 2x, right? So it's not 45, it's sharper than 45, right? Y equals 2x, and then y equals 1 is this line here, right? So this is what this looks like looking down. So when we think about calculating this triple integral, the choices are, in what order are we going to compress things? So we're going to compress in the z direction first, because we have an upper surface, z equals 1 minus y squared, a lower surface, z equals 0. Here, I'll set these limits over here as we do this problem. So we're going to take z between 0 and 1 minus y squared. That's the one we're going to do first. Yeah. The second one, so now when we're looking at something in the xy plane, well, we want to do it in the x direction now because I have a lower limit for x and a single upper limit for x. If you wanted to integrate y, you'd have to do it in two pieces, because here the lower limit would be y is 0, upper limit is y equals 2x, and here the lower limit would be y equals 0, y equals 1. So there's two different limits there. You'd have to have a sum of two integrals. So we'd like to do this just in one. So if we think of doing x next, its lower limit would be x equals 1/2 y, just solving this for x. Its upper limit would be 3. So we'll do the x as the next integral, which we don't always do. And then finally, we'll integrate y. Where's y go to? Once we've squished this down, y just goes, squished it in this direction, then y goes from 0 to 1. Okay. That's the work in setting up this integral. The rest of it is kind of easy. Okay, so let me just, I'll keep this picture here, and I'll work around it. I'm going to erase this guy, but we'll leave the diagram. Okay, so, well here, so our volume integral will be, okay, our triple integral of d dv. We don't need to write that part, but that's what we're doing. And this is going to be, the outermost is the last one, 0 to 1 will be dy. And then we have y over 2 to 3. Then we have 0, 1 minus y squared. Integrand of 1. And then we have what order? So dz, dx, dy. As in general, we have now our limits of integration here. In this case, is a function of x and y. Yeah, there's no x dependence, but in principle, this is a function of x and y. This next one is a function only of y, and it is. Here's y over here, it happens to be a constant. The last one cannot be a function of x, y, or z. So your last one needs to be just a single constant limits of integration. Okay. So executing this out is pretty easy. Y over 2, 3. So that we just get z here. Z from, I'm just doing this really slow, 0. So that looks like 0 to 1, y over 2 to 3, 1 minus y squared, oops, dx dy. Yeah. Now right away you might go, oh, wait a minute, something's wrong. Like, I've only got y's here, I'm integrating x. Yeah, that's true. That's true. So this next integral is easy. It's 0 to 1, and then we have, okay, well, x minus x y squared from 3 to y over 2. And then that final thing is dy. So now, right, because I integrate this is a constant, it's really just x times 1 minus y squared, right, obviously. So this thing is 0 to 1, and then we have, let's do it, so 3 minus 3y squared minus y over 2 minus plus, so plus y over 2 squared. Okay, so I just went 3, so 3x minus 3y squared minus y over 2 minus y over 2y squared. Okay, so all the x's replaced with those limits, as always. Now I'm just going to move back over here to keep the diagram the same. So our volume will be equal to I'll simplify one time. 0, 1, I've got 3 minus 3y squared minus 1/2 y plus 1/2 y cubed dy. Okay, so this becomes 3y minus 3y squared over 2, so y cubed, so 3y cubed over 3 minus y squared over 2, so minus y squared over 4 plus 1/2 y to the 4 over 4 from 1 to 0. So the 0 one's going to cancel off, so this is just 3 minus 1 minus 1/4 plus 1/8. Right? So that is equal to, all right, we got 2 minus 2 over 8 plus 1 over 8 equals 16 over 8 minus 1 over 8 equals 15 divided by 8. Okay, 15. That's our answer. Okay, doesn't have units because we don't have any coefficient relating anything to anything. In the spirit of making sense of it, as usual, right? It's a volume integration. We expect this number to be positive. It is positive, so that's good. Hard to make a lot more sense of it. It probably makes sense as greater than 1. We've got x out here to 3, z goes up to 1, y goes up to 1, so it should be bigger than 1, on the order of, a couple or something like that. And actually it is on the order of 2, so okay, that makes sense. If it was 10,780, that'd be weird. If it was 1 divided by 150 pi, that'd be weird, right? But this sort of feels right, positive number. That's an example. So that's the first example of triple integration, just in the context of a volume integral. Next thing we'll move on to is a more general triple integration. Then we'll look at different coordinate systems and divergence there.